This paper settles the pass complexity of approximating maximum matchings in dynamic graph streams via semistreaming algorithms. The authors present a randomized sketching-based semistreaming algorithm for O(1) approximation of maximum matching in dynamic streams using O(log n) passes. This exponentially improves upon several O(log n) pass algorithms developed for this problem since the introduction of the dynamic graph streaming model. The algorithm is based on a model-independent reduction from matching to maximum independent set, MIS. The authors first present a prior work in ACG +1-5, Vel 24, and then introduce their dynamic streaming algorithm for matchings. The algorithm uses a random-order greedy approach and is implemented using a sketching and streaming toolkit. The authors also prove that any semistreaming algorithm for O(1) approximation of maximum matching in dynamic streams requires log n passes. This is the first multipass lower bound for this problem, which is already optimal, settling a long-standing open question in this area. The lower bound is based on the hierarchical embedding technique of AKNS24, and uses information theoretic arguments to address challenges in applying hierarchical embeddings for approximate matchings. The paper also provides a technical overview of the upper and lower bounds, including a discussion of the challenges and techniques used to address them. The authors use concentration inequalities, sketching and streaming toolkit, and two-party communication complexity to prove their results. The paper's contributions include settling the pass complexity of approximating maximum matchings in dynamic graph streams, presenting a randomized sketching-based semistreaming algorithm for O(1) approximation of maximum matching, and proving a lower bound of log n passes for any semistreaming algorithm. The paper's techniques include a model-independent reduction from matching to MIS, a random-order greedy algorithm for matching, and information theoretic arguments for the lower bound. The paper's results have implications for the design of efficient algorithms for dynamic graph streams and provide a better understanding of the limitations of semistreaming algorithms for this problem. The paper's techniques and results can be applied to other problems in dynamic graph streams and have the potential to lead to new breakthroughs in this area. The dynamic graph streaming model involves processing a graph with vertices v and edges e, defined by a sequence of insertions and deletions in a stream sigma of length n, where each entry sigma I is either inserting or deleting an edge. The goal is to make one or a few passes over the stream, using limited memory, and compute the answer to a given problem on the graph G at the end of the last pass. This paper focuses on the maximum matching problem in this model. Previous work on this problem has led to the development of O(1) approximation algorithms and O(log n) pass semistreaming algorithms for dynamic graph streams. However, there is a significant gap between the upper and lower bounds for dynamic streaming matchings. This paper aims to settle the pass complexity of O(1) approximation of maximum matching in dynamic streams by improving both the upper and lower bounds. The authors present two main results. Result 1 shows that there is a randomized log n pass O(1) approximation semistreaming algorithm for the maximum matching problem in dynamic streams. This result holds even for 1 plus epsilon approximation of weighted, general, matching for any constant epsilon greater than 0. The algorithm relies on different techniques compared to prior work on this problem. Result 2 establishes that any randomized semistreaming algorithm for O(1) approximation of maximum matching in dynamic streams with constant probability of success requires log n passes. This lower bound holds even on unweighted bipartite graphs. The authors also improve the single-pass lower bounds of previous work all the way to log n passes. The paper's contributions include exponentially improving the pass complexity of different algorithms developed for this problem and establishing the optimal pass complexity of approximate matchings in dynamic graph streams as log n passes. The results also contribute to the line of work on multipass semistreaming lower bounds, which has been a challenging question in the field. In the realm of dynamic graph streaming algorithms, a novel approach has been developed that leverages the graph sketching technique to achieve an O(1) approximate matching in log n rounds with n size sketches. This result is significant as it implies a massively parallel computation (MPC) algorithm for approximating matchings in O log n rounds, using machines of EO n memory and only EO n working memory. Prior work in this area achieved MPC algorithms with similar guarantees using various other techniques. The upper bound of this approach utilizes the O log n pass semistreaming algorithm for maximal independent sets (MIS) as a subroutine and draws inspiration from recent work that relates MIS to the vertex cover problem. The lower bound builds on and adapts the recent communication complexity techniques developed for proving an omega log n pass semistreaming lower bound for MIS. The first main technical ingredient of the algorithm is a model-independent reduction from O approximate fractional matchings to the randomized greedy MIS algorithm. This reduction is inspired by the work of Veld-24, which showed that the complement of the randomized greedy MIS is a 2 approximate vertex cover in expectation. The second main technical ingredient is a partial implementation of the above reduction in O log n passes of dynamic streams, relying on the semistreaming implementation of the randomized greedy MIS in O log n passes by ACG plus 1.5. The lower bound follows the recently developed hierarchical embedding technique of AKNS24, which creates hard instances for PPASS streaming algorithms for a problem P by embedding many P-1 pass hard instances of P in a single graph G. The key differences in implementing this strategy compared to AKNS24 include the combinatorial construction of hard instances using edge deletions following the approach of DK20, and the information theoretic arguments, which require careful sharing of the input of players with each other to guarantee that no not inserted edge gets deleted. The technical overview of the paper provides a streamlined explanation of the main ideas and approach. The algorithm builds upon two prior works, the dynamic streaming MIS algorithm of ACG plus 1.5, and the model-independent reduction of Veld-24 from vertex cover to randomized greedy MIS. The former algorithm simulates the randomized greedy MIS in batches, leveraging the residual sparsity property to reduce the effective degree of vertices. This allows for an O log n pass semistreaming algorithm that faithfully simulates the randomized greedy MIS. The model-independent reduction of Veld-24 shows that the complement of the randomized greedy MIS is a 2 approximate vertex cover in expectation. This result is obtained through an elegant application of LP duality, where the probability of an edge being blocking is used to define a fractional matching. The assignment of probabilities to edges yields a 2 approximate fractional matching, implying that the vertex cover is a 2 approximate vertex cover. The combination of these two works implies a semistreaming algorithm for finding a 2 approximate vertex cover in dynamic streams. However, extending these ideas to matching is challenging. A similar reduction for matching is not straightforward, as the fractional matching introduced in Veld-24 is only an analysis tool and not an actual matching. The algorithm can identify blocking edges, but these edges are far from forming a matching. The paper highlights the challenges of extending these ideas to matching and discusses how to address these challenges. The technical overview provides a foundation for understanding the subsequent sections of the paper, which delve into the technical arguments and details of the algorithm. The discussion of prior work and the model-independent reduction sets the stage for the development of new ideas and techniques for solving the matching problem. The proposed approach involves designing a new scheme for finding a fractional matching from a single run of the randomized greedy MIS algorithm. The scheme assigns a value of 1 deg v to every edge v w, with deg w is less than or equal to deg v whenever a vertex versus joins the vertex cover C. This assignment is illustrated in Figure 2, which shows the blocking edges, the vertex that joins the MIS, and its neighbors that join the vertex cover. The assignment is designed such that the total x-value incident on any vertex is not much more than 1, allowing for a rescaling to obtain a fractional matching. The key observation is that in each iteration of the algorithm, if the expected borrowed assignment by a vertex is high, then this vertex also has an equally high chance of being removed from consideration after this iteration. The expected borrowed assignment of a vertex W in an iteration is bounded by the probability of W being removed in that iteration, as shown in equation 3. This leads to a probabilistic question of upper bounding the total borrowed assignment of a vertex W over all iterations, subject to the condition that the expected loss in each step is upper bounded by the probability of terminating the experiment at that step. However, the variables xw_i can be unboundedly large, making it challenging to achieve the desired bounds. The technical condition in the assignment of x, which only assigns a value of 1 deg v to an edge v w, if deg w is less than or equal to deg v, is crucial in bounding the expectation and variance of the problem. The analysis shows that the expected total borrowed assignment of a vertex W is bounded by a constant factor, and the variance is bounded by an O(1) factor of the expectation. Using Chebyshev's inequality, it can be shown that the expected overflow of the assignment x can be bounded, allowing for a fractional matching to be obtained by trimming down x by a constant factor. The resulting fractional matching is an O(1) approximation in expectation, as shown by the duality of matchings and vertex covers. However, the actual definition of X requires a more careful analysis to obtain an approximate version of equation 2, which is sufficient for the primordial analysis. The proposed approach provides a lightweight reduction for finding an O(1) approximate fractional matching in expectation from a single execution of the randomized greedy-Mies algorithm. The paper discusses the development of a dynamic streaming algorithm for matchings, which is an extension of the semistreaming implementation by ACG+15. The main challenge lies in incorporating the reduction from fractional matchings to randomized greedy-Mies into this algorithm. The authors outline 3 key challenges: large support in fractional matchings, determining neighbors of a vertex joining the vertex cover, and determining which edges receive fractional matchings. To address these challenges, the authors propose several solutions. First, they use a standard trick to sample each edge of the graph independently with probability asymptotically equal z lane n, where z is the value of the edge in the fractional matching. This allows them to recover a large enough matching. Second, they augment the semistreaming algorithm to add a timestamp t, v, to each vertex versus that joins the vertex cover, which helps in identifying the set of its neighbors still present in the graph when versus joins the vertex cover. The authors also propose a method to compute these time stamps using the residual sparsity property of the randomized greedy-Mies. They partition each batch into O, log n, subbatches and prove that, with high probability, for every vertex v, the first subbatch containing at least one neighbor of v in E can only have log n neighbors of v in total. This property allows them to recover the time stamps of all vertices using O(1) passes and O(n) poly log n space. Finally, the authors delegate some computation of the fractional matching in the reduction to the analysis. They compute the time stamps and sample asymptotically equal log n deg v fraction of remaining neighbors of versus the total number of edges sampled. This way will be asymptotically equal n log n edges, and they can find them using a sparse recovery approach. The rest of the algorithm involves returning a maximum matching of these sampled edges and performing a simple rejection sampling idea to recover a subsampled version of the fractional matching X in the reduction. The authors present a lower bound for dynamic streaming algorithms that solve the maximum matching problem. They utilize the hierarchical embedding technique, recently developed in AKNS24, to prove an omega log n pass lower bound for finding a maximum matching in a dynamic streaming setting. This technique involves constructing a hard instance for PPASS streaming algorithms by embedding a collection of P1 pass hard instances inside a single graph. The algorithm must then solve a special subset of these instances, which are hidden in the first pass, to find the maximum matching. The authors adapt this technique to prove a dynamic streaming lower bound, as opposed to insertion-only ones, and address the challenges that arise in this adaptation. They borrow ideas from prior work in DK20 and AKZ24 to construct hard instances of the problem and analyze them using information theoretic tools. The lower bound relies heavily on communication complexity arguments, and the authors provide a brief overview of this technique and its connection to streaming. The hierarchical embedding technique works by constructing a graph G that contains a collection of P1 pass-hard instances, which are put together in a way that forces the algorithm to solve a special subset of these instances without revealing their identity in the first pass. The authors prove that any algorithm must either spend omega AB space to learn non-trivial information about all subinstances or spend its first pass learning the identity of the special instances and then solve them independently in the remaining P1 passes. The authors derive a lower bound on the space required for solving the maximum matching problem, which implies an omega log n pass lower bound for semistreaming algorithms. They also discuss the challenges of formalizing this idea, including combinatorial and information theoretic aspects, and refer to AKNS24 for more details. The authors mention the additional challenges of applying this technique to prove a dynamic streaming lower bound for O1 approximation of matchings. The paper discusses the challenges of applying hierarchical embeddings for approximate matchings in dynamic streams. It highlights two main challenges: combinatorial aspects and information theoretic aspects. The authors address these challenges by borrowing ideas from previous works, such as DK20 for combinatorial constructions and AKZ24 for information theoretic arguments. The first challenge is related to the requirement that a majority of edges in all large matchings should come solely from special hidden instances. This is too stringent and can only be achieved if the graph contains n edges in total. Instead, the authors use an idea due to DK20 for proving single-pass O1 approximation lower bounds for matchings in dynamic streams. This allows them to let go of the group structure of subinstances and create an instance that involves only one induced set of P1 pass instances. The second challenge is related to the information theoretic aspects of O1 approximate matchings. The authors need to ensure that the edges deleted in the second half of the stream already have appeared in its first half, which breaks the independence properties used in AKNS24 for their information theoretic arguments. To address this, they borrow ideas from AKZ24 for augmenting the input of players even for multi-round pass algorithms on dynamic streams. The authors then discuss their fix to the first challenge, starting with an overview of the prior work of DK20. They use a communication problem where Alice receives an n times n matrix A encoding the bipartite adjacency matrix of a random bipartite graph G between two sets of vertices L and R, each of size n. Bob receives random permutations of n that reorder rows and columns of A, and a submatrix B of A. The input graph G at the end of the stream is the bipartite graph on bipartition L and R and edges 1, Adele. This graph has an induced matching M of size n, 2 n, with high probability and a vertex cover of size n. Any O1 approximate matching algorithm on the graph 1, Adele needs to recover many edges of M. In DK20, it was shown that given only A and without the knowledge of sigma rand and sigma c, the majority of edges in 1 have an equal chance of appearing as the edges of the induced matching M. Thus, from Alice's perspective, most edges in 1 can become important in finding a large matching in 1, Adele. Hence, Alice needs to communicate omega n squared bits before Bob can output an O1 approximate matching in the graph. The authors present a multi-pass lower bound construction for the augmented hidden matrices AHM problem, a two-player communication problem inspired by the construction of DK20. The construction involves creating a hard instance of AHM by hierarchically embedding many instances of AHMR1 into a larger instance of AHMR. The embedding technique is used to create a graph G consisting of a collection of induced hard R1 round instances, which are then used to define the edges to be inserted and deleted from the graph. The construction begins with a TRXTR matrix of R1 hard instances, where each instance is an AHMR1 problem on NR1 vertices. The matrix A is then defined by plugging the matrix B, R1, I, J between group I of rows and group J of columns. The matrix B is defined by picking two random permutations of the row groups and column groups of the matrix A, and then applying these permutations to the instance matrix I. The authors argue that the constructed instance of AHMR is hard because it contains a large induced subgraph consisting of vertex disjoint copies of hard, R1, round instances. Any O(1) approximate matching algorithm needs to find large matchings from many of these instances, effectively solving them. The authors also analyze the parameters of the construction, showing that the communication space needed to solve the instance is at least min T2R, TR, SR1, NR1, where SR, NR, denotes the communication space needed for solving AHMR on NR size instances. The construction is illustrated in Figure 6, which shows the matrices A and B and the underlying graph G. The authors also provide an intuition behind why the constructed instance should be hard, arguing that the graph G contains a very large induced subgraph consisting of vertex disjoint copies of hard, R1, round instances. The authors establish a lower bound on the number of rounds required by EO(n) communication protocols for the approximate hypergraph matching (AHM) problem. They use the lower bound of dk20 as a base case and prove that SR(n) n1 plus half an ohm R, implying that omega log n rounds are needed for AHM rand omega log n passes are needed for semistreaming algorithms for O(1) approximation of matchings. The input to Alice and Bob in the AHMR A-B problem is partitioned such that Alice receives the matrix A and Bob receives the submatrix B. However, due to the recursive nature of the instances, the partitioning is more complex. Roughly speaking, Alice receives all the B's and Bob receives all the A's, and additionally the B's on the off-diagonal submatrix. This partitioning allows Alice to insert all edges in B and Bob to delete all edges inserted by Alice in the off-diagonal instances, creating the inducedness property. The authors then discuss the theoretic arguments for the hardness of their instances. They revisit the one-round lower bound of dk20 and provide a new proof that shows none of the diagonal entries of B can be revealed by Alice's message. This is done by considering the input permutations sigma R and sigma C given to Bob and defining two sets of rows and columns, tro and tcol. They show that providing Bob with a tro tcol gives him more information than his original input in the off-diagonal entries of B. However, conditioned on the choices of tro and tcol, the special entry A, sigma R, n-I plus j, sigma C, n-I plus j, is chosen uniformly from all unfixed entries of A. This is sufficient to prove that a message of size much less than n-tro, n-tcol, cannot reveal more than 1 bits about the special entry Bob needs to output. The authors note that this type of chain rule argument has appeared in similar contexts elsewhere. They also mention that their way of partitioning the input has appeared recently in the multipass dynamic streaming lower bound of AKZ24 for MSTs. The paper discusses a multi-round lower bound for the all-or-nothing hidden matrix AHM problem, which is a fundamental problem in communication complexity. The authors present a three-step approach to prove this lower bound, following the general round elimination argument introduced by AKNS24. However, their approach differs from AKNS24 in the nature of the direct sum argument used in Step 1 and the compression technique used in Step 2. Step 1 involves turning in round protocol pi r for AHMR with communication cost s to in round protocol pi 1 r for solving AHMR1 with communication cost s but information cost s trail. This step uses internal information cost direct sum arguments, as opposed to external information in AKNS24. The authors outline this process by sampling J element of I star operator and all off-diagonal induced instances, embedding the given instance of AHMR1 at the JTH diagonal entry of the special induced instances, and sampling one part of the input publicly and the other privately for every remaining instances. Step 2 transforms the round protocol pi 1 r for AHMR1 with information cost s tr to in round protocol pi 2 r for solving AHMR1 with communication cost s tr poly r. This step is based on existing message compression arguments that allow for compressing the communication of a limited round protocol down to its information cost. The authors use the compression technique of 16 Japanese yen for for internal information cost, whereas AKNS24 uses HJMR07 for external information. Step 3 turns the round protocol pi2r for AHMR1 with communication cost STR poly r to an R1 round protocol pi R1 for solving AHMR1 with the same communication, while incurring an additional O1 additive factor on error probability as long as S much less than T2R. This step is the real round elimination step, where the authors finally obtain an R1 round protocol. The additive factor in the error probability comes from a similar argument as their one round lower bound outlined above. After these steps, the authors obtain that as long as S much less than T2R, the resulting R1 round protocol pi R1 for AHMR1 succeeds with a non-trivial probability. Given the communication cost of pi R1 is S, TR poly R, they obtain that either ST2R or S1 poly R TRSR1, NR1, which establishes the desired lower bound of N1 plus half an ohm, R, communication for round protocols for AHMR. This in turn implies that any PPASS streaming algorithm for O1 approximation of matchings requires N1 plus half an ohm, P, space. In particular, semistreaming algorithms require omega, log n, passes as desired. In this paper, the authors present a comprehensive study on the use of sparse recovery algorithms in graph sketching. They begin by introducing the necessary notation and definitions, including the concept of a graph, its vertices, edges, and the maximum matching size. The authors also discuss the concept of a fractional matching, which is an assignment of values to the edges of a graph such that each vertex has a total value of at most 1. The paper then delves into the topic of concentration inequalities, specifically the Chernoff bound and its extension to negatively correlated variables. This is followed by a discussion on limited independence hash functions and their application in extending Chernoff bounds. The authors then introduce the concept of sparse recovery algorithms, which are used to recover sparse vectors from a dynamic stream. They provide a detailed description of these algorithms, including their space complexity and the probability of success. The authors also note that the use of sparse recovery algorithms in graph sketching dates back to the seminal work of AGM12, and that many dynamic streaming algorithms use a particular application of sparse recovery in the form of L0 samplers. Finally, the authors discuss the implications of these results for graph sketching and provide a comprehensive toolkit for practitioners working in this field. This includes a detailed description of the algorithms, their space complexity, and the probability of success, as well as a discussion on how these algorithms can be applied in real-world scenarios. In the context of machine learning and artificial intelligence, the paper discusses various techniques for sketching and streaming tools for matchings in graphs. It highlights the use of vertex sampling approaches to reduce the number of vertices in a graph while preserving its largest matching approximately. This method is crucial for finding matchings in dynamic streams in a single pass. The paper also discusses the boosting framework for improving O1 approximation algorithms to 1 plus epsilon approximation algorithms in dynamic streams. Furthermore, the paper delves into two-party communication complexity, providing definitions and explanations of key concepts such as communication cost and information cost. It establishes a connection between communication protocols and streaming algorithms, showing how a PPASS space streaming algorithm can be translated into a two-party protocol with two P1 rounds and OPS communication cost. Additionally, the paper discusses message compression techniques to reduce the communication cost of limited round protocols close to their information cost. This is achieved through a simplified version of JPY16, Theorem 3.4, which allows for simulating any round protocol pi with error at most epsilon in rounds by a protocol pi, with communication at most CJPR, epsilon IC, pi, micro, plus R2, epsilon. Overall, the paper presents a comprehensive overview of techniques for sketching and streaming tools for matchings in graphs, along with insights into two-party communication complexity and message compression. These concepts are crucial for understanding and improving algorithms in machine learning and artificial intelligence. The paper presents a randomized greedy algorithm for finding an approximate fractional matching in a graph by growing a random maximal independent set, MIS. This algorithm is the core of the approach and is provided in a model-independent manner. The algorithm can be implemented in dynamic graph streams as an OO, log n, pass semistreaming algorithm. It can also be improved to yield an approximation factor of 1 plus epsilon and prove the following theorem, which formalizes result 1. The algorithm follows the strategy of VEL24 by computing a random order greedy MIS and letting its complement be a vertex cover. Whenever the algorithm inserts a new vertex into the vertex cover, it also puts a certain fractional mass distributed uniformly on some subset of the not yet covered edges incident to this vertex. At the end, the algorithm further trims down these fractional values to turn them into a fractional matching, by reducing the mass on every vertex to become at most 1 explicitly. The main properties of this algorithm are captured in Theorem 2, which provides separate guarantees for the assignments x and y. Given any graph G and parameter beta less than 1/8, algorithm 1 outputs an integral vertex cover V cover, an intermediate solution x element of Re, and a fractional matching y element of Re such that x element of x beta, 2 V cover. This implies that the fractional matching y returned by the algorithm is a multiplicative approximation in terms of beta. The proof of Theorem 2 starts by defining several variables related to the iterations of the while loop in algorithm 1. For each iteration t element of t of the while loop, the variables g, t, n, t, m, t, u, t, v, t, cover, n, t, v, deg, t, v, x, t, e, and r less than t are defined. The first lemma relates the expected size of the vertex cover computed by algorithm 1 and the intermediate solution x that it computes, thus proving EQ 6 in Theorem 2. The analysis of the algorithm's performance continues with the derivation of a lower bound for the expected value of the solution. Specifically, it is shown that for any choice of the random bits $r less than $t, the expected value of the solution $x is at least $beta, CDOT2, CDOTE, V, T, underscore, cover, r less than $t. This result is obtained by combining two equations, one of which relates the expected value of the solution to the expected value of the number of vertices in the cover, and the other of which relates the expected value of the number of vertices in the cover to the expected value of the solution. The proof of this result relies on the definition of the algorithm and the properties of the indicator function. It is also shown that the size of the solution $x is sufficiently large, but not necessarily a fractional matching. Therefore, the update in line 3 of the algorithm is necessary to trim down $x into a fractional matching $y. The main step of the proof is to show that this step does not reduce the size of $x dramatically, proving EQ 7 in Theorem 2. To continue the analysis, additional notation is introduced. For any iteration $t, GEQ1, the value $x, t, underscore v is defined as the sum of the values of the edges incident to vertex $v at iteration $t. The values $out, t, underscore v and $in, t, underscore v are also defined, representing the value added to $x, t, underscore v by vertex $v itself and by other vertices, respectively. It is shown that $x, t, underscore v equals out, t, underscore v plus in, t, underscore v and that $out, t, underscore v is non-zero in at most one iteration. The analysis then focuses on bounding the value of $in, t, underscore v across the iterations. It is shown that the total sum that can be assigned to vertex $w across the iterations is upper bounded by beta in expectation. This result is proved in a more general form, which corresponds to setting $t equals $0. The proof relies on the definition of the algorithm and the properties of the indicator function. Here is a combined summary of pages 31 and 32 of the research paper. The authors derive an upper bound on the expected value of in t underscore w which represents the total value assigned to vertex W at iteration T. Specifically, they show that E in T underscore W R less than T is less than or equal to beta PR E underscore W T R less than T where E underscore W T is the event that W is removed from the graph G T at iteration T. This inequality implies that if in T underscore W is expected to be large, then there is a good chance that W will be removed from G T and no longer receive value in subsequent iterations. The authors then formalize this intuition by showing that E x underscore T is greater than or equal to T in T underscore W R less than T is less than or equal to beta where x underscore T is the indicator variable for the event that W belongs to G T after iteration T. This result is obtained by applying the law of total expectation and using the previously derived upper bound on E in T underscore W R less than T. The authors also establish an upper bound on the value of in T underscore W in any iteration T, showing that in T underscore W is less than or equal to beta . This result is used to bound the variance of the total value assigned to W which is shown to be at most 3 beta E x underscore T is greater than or equal to 1 in T underscore W . The authors then use this variance bound to derive a concentration inequality for the total value assigned to W . Specifically, they show that PR x underscore T is greater than or equal to 1 in T underscore W greater than theta is less than or equal to 3 beta beta squared E x underscore T is greater than or equal to 1 in T underscore W where theta is greater than or equal to 1 beta . This result is obtained by applying Chebyshev's inequality and using the previously derived variance bound. Overall, the authors establish a series of technical results that provide insight into the behavior of the algorithm and the values assigned to vertices. These results are used to derive concentration inequalities that bound the probability of large deviations in the total value assigned to a vertex. The paper discusses the design and analysis of a new algorithm for the maximum independent set (MIS) problem in dynamic streaming graphs. The algorithm is based on a combination of the randomized greedy MIS algorithm and a novel dynamic streaming implementation. The authors provide a detailed analysis of the algorithm's performance, including its approximation ratio and time complexity. The paper begins by introducing the MIS problem and its importance in various applications. It then describes the randomized greedy MIS algorithm, which has been shown to achieve a good approximation ratio in static graphs. The authors extend this algorithm to dynamic streaming graphs, where the graph is revealed over time and vertices can be processed only once. The dynamic streaming implementation of the algorithm is based on processing the graph in batches of vertices with growing sizes. A key new subroutine allows the authors to determine the time stamp of all vertices, indicating in which iteration of the while loop each vertex was removed. This is done via algorithm 2, which finds the set vcover in algorithm 1 and assigns a timestamp to each vertex. The authors provide a detailed analysis of the performance of algorithm 2, including its approximation ratio and time complexity. They show that the algorithm achieves a good approximation ratio and has a low time complexity, making it suitable for large-scale dynamic graphs. The paper concludes by discussing the implications of the results and potential future directions for research. In summary, the paper presents a new algorithm for the MIS problem in dynamic streaming graphs, which combines the randomized greedy MIS algorithm with a novel dynamic streaming implementation. The authors provide a detailed analysis of the algorithm's performance and discuss its implications and potential future directions. Here is a combined summary of the 2 pages. The analysis of algorithm 2 relies on a greedy approach, where vertices in vcover are added after processing a batch, but for the purpose of analysis, they can be considered immediately after processing a vertex (u). Notation is introduced to describe the random variables in algorithm 2, including (gi). The graph stored in batch (i), (ni). The number of vertices in (ui), and (ni), (w). The neighborhood of vertex (w) in graph (gi). A helper lemma, lemma 4.8, is proved to bound the space complexity of algorithm 2. This lemma, originally due to ACG plus 1,5, states that with high probability, the maximum degree of (gi) is bounded by (100), ni 1, lane, n. The proof involves considering the sampling process of vertices in (ui) and bounding the probability of a vertex having a high degree. Claim 4.9 states that line 2b of algorithm 2 can be implemented in (o) n log squared n space with high probability. The proof involves bounding the maximum degree of (gi) using lemma 4.8 and then using a sparse recovery algorithm to recover all edges of (g) ui vcover union v-mis. Algorithm 3 is introduced to find the timestamps in line 2d of algorithm 2. This algorithm partitions the set (ui) into groups based on geometrically increasing sizes and defines indicator vectors (phi, v, j) for each vertex (v) and group (j). A randomized (q) sparse recovery algorithm is then used to test if (phi, v, j) is (q) sparse or not. Lemma 4.10 states that algorithm 3 finds the timestamps in line 2d of algorithm 2 with high probability and can be implemented in (o) n log cubed n space. The analysis of algorithm 2 relies on a combination of greedy and probabilistic techniques to bound the space complexity and find the timestamps. The use of sparse recovery algorithms and indicator vectors enables the efficient implementation of the algorithm. Algorithm 3's correctness is established by demonstrating that it finds the required timestamp t, v, with high probability for any vertex v element of v, v-mis. The algorithm's performance is analyzed by considering the smallest index j star operator element of b, where parallel phi, v, j star operator, parallel 0 greater than 0. If no such j star operator exists, v is not a neighbor to any vertex in v-mis and will not be added to vcover. Otherwise, the neighbor u of v in v-mis with the smallest value of t, u, belongs to ui, j star operator, and returning such u is the correct answer. The algorithm's error sources are identified, including the randomized sparse recovery's potential failure to retrieve phi, v, j, for all v in v, v-mis and j element of b. Using the union bound, it is shown that this event happens with probability at least 1-n-198 for the choice of delta equals n-200. Claim 4.11 is introduced to bound the probability that parallel phi, v, j star operator, parallel 0 greater than q. The claim states that for any j greater than 1 and any vertex v element of v, v-mis, if parallel phi, v, j minus 1, parallel 0 equals 0, then parallel phi, v, j, parallel 0 less than slanted equal q with high probability. The proof involves defining useful notation, such as gi, j, dj, v, and key, j, and using Chernoff bounds to argue that with high probability, the sparsity of phi, v, j, is at most q. The case when dj, v, 100 lane n, pj is also analyzed, and it is shown that dj, v, 25 ln pj-1 in all cases. This leads to the conclusion that j cannot be the first index with non-empty support in phi, v, j, and claim 4.11 is established. The proof is finalized by arguing that if j equals 1, ui, 1 has only 2 vertices and phi, v, 1, is too sparse. For any j greater than 1, claim 4.11 is used to argue that for any vertex v, phi, v, j star operator, is q sparse with high probability. This proves the correctness of the algorithm. The space complexity of the algorithm is also analyzed, and it is shown that for every V element of V, O, log 3n, space is needed to maintain O, lone, randomized sparse recovery algorithms. This leads to a total space complexity of O, nlog3n. The reduction of algorithm 1 is used to recover a large matching from the input graph. The algorithm allows for the recovery of timestamps of all vertices in a single run of the randomized greedy Ms algorithm in O. Log n passes over a dynamic stream. The goal is to sample the edges of the graph with probabilities proportional to their y values and use the sampled edges to find a large matching. The authors aim to sample each edge of the graph with probability pay, but face the challenge of not being able to recover the values of y, or even x, explicitly and learn pays. To address this, they use a proxy for them algorithmically. They start by utilizing the time stamps of all vertices to find the degrees of all vertices at the time they are settled, as stated in observation 4.12. This observation allows them to assume they have the remaining degree of every vertex V at the time it is settled, fixing the value x will assign to the edges of verses. However, they still lack sufficient information to perform the check-in line, 2c, of algorithm 1 to know which incident edges of V receive a non-zero fractional matching. To sidestep this issue, they define an intermediate assignment z element of R(e), which can be explicitly found for any pair of vertices. The vector z is defined as zuv equals 200 log n, deg, t, vert, u, v, vert, u, v, where vert, u, v, is the vertex to which the pair, u, v, is assigned, as per definition 4.13. The authors then show the relevance of z values in claim 4.15, which states that for every edge E element of E, pay is less than or equal to z, where pay element of 0, 1, is from EQ, 14. This claim is proven by arguing that z is less than or equal to beta, deg, t, vert, e, where z is updated in at most one iteration of the loop in line 2c of algorithm 1. Given claim 4.15, the authors can sample the edges with probability proportional to z values, which can be computed. They propose a two-step sampling process. First, sample all pairs, u, v, based on their value zu, v to obtain a vector phi z element of R(v squared), and then maintain a sparse recovery algorithm over phi z to recover the actual edges inside this sample. The sampling is done using a kappa-wise independent hash function, where kappa equals 200 log n. The authors present a novel approach to finding a large matching in a graph, leveraging a combination of sampling and rejection sampling techniques. They define a set phi z of pairs, u, v, such that h, u, v, is less than or equal to min 1, zu, v, where h is a kappa-wise independent hash function and zu, v is a probability value. The incidence vector phi z of Ez, the intersection of E and phi z, is then obtained by sampling each edge E and E with probability z. The authors prove that the size of Ez can be bounded with high probability, specifically, Ez equals O, n log n, using a combination of propositions 3.4 and 3.5. This is achieved by showing that the number of edges assigned to each vertex V, denoted by a, v, is O, log n, with high probability. The authors then define an indicator random variable z for each edge E in A, v, which is 1 if E is sampled and as. By applying proposition 3.5, they bound the probability that the number of sampled edges in A, v, exceeds 400 log n. The authors then relate the sampled edges Ez to a fractional matching y obtained from algorithm 1. They define an alternative sampling process for obtaining a set EP, which is a subset of Ez. By rejecting edges with pay less than h, E, is less than or equal to z, they show that EP contains a fractional matching with expected size approximately equals y. This is achieved by defining an assignment y asterisk operator E for each edge E and E, which is supported only on the edges in EP. The authors then prove that y asterisk operator can be scaled to become a fractional matching, implying that EP contains a fractional matching with expected size approximately equals y. The authors conclude that the expected size of the matching in EZ is at least 1,8 beta, 1,2 beta, beta, 10, micro, G, where micro, G, is the size of the maximum matching in G. This result is obtained by applying the law of total expectation and leveraging the correctness probability of algorithm 2. In the context of machine learning and computer science, the paper discusses a novel approach to solving the maximum matching problem in a graph. The authors propose an algorithm that uses a combination of vertex sampling and sparse recovery techniques to achieve a high probability bound on the approximation ratio of the algorithm. The paper begins by defining a fractional matching and its relationship with the maximum matching problem. It then introduces the concept of a dynamic streaming algorithm, which is used to solve the maximum matching problem in a graph. The authors provide a detailed analysis of the algorithm's performance, including its space complexity and approximation ratio. The authors also discuss how to boost the probability of success of the algorithm to a high probability bound. This is achieved by using the vertex sampling approach of proposition 3.7 for O, log n, guesses of micro, G, as powers of 2 between log 2, n, to n and running the algorithm for each guess separately in parallel. In conclusion, the paper presents a new approach to solving the maximum matching problem in a graph using a combination of vertex sampling and sparse recovery techniques. The proposed algorithm achieves a high probability bound on the approximation ratio, making it a significant contribution to the field of machine learning and computer science. In the context of machine learning and computer science, the paper discusses a novel algorithm for finding a maximum matching in a graph using a dynamic stream. The algorithm is designed to work in the semistreaming model, where the input graph is presented as a sequence of edges and the algorithm must process this sequence in a single pass while using a limited amount of memory. The proposed algorithm first samples a subset of vertices from the graph and then finds a matching within this subset. This process is repeated multiple times to obtain an approximation of the maximum matching. The authors show that with high probability, their algorithm can find a matching that is at least half the size of the maximum matching. The paper also presents a lower bound on the number of passes required by any semistreaming algorithm to approximate the maximum matching problem with high probability. This lower bound is achieved through a connection between the streaming and communication models, using a new two-party communication problem called augmented hidden matrices, AHM. The authors prove that any round protocol that solves AHM with a certain probability of success must have a communication cost of at least a specific value. They then construct graph instances corresponding to the AHM problem and show a connection between any PPASS dynamic streaming algorithm for approximate maximum matching in AHM, where R equals 2p1. Finally, the authors use these lemmas to prove their main theorem, which states that any semistreaming algorithm that computes a constant approximate maximum matching on a bipartite graph with high probability requires at least log n passes. This result provides a fundamental limit on the efficiency of algorithms in the semistreaming model for solving the maximum matching problem. In the context of dynamic streaming algorithms, the paper discusses the lower bound on the space complexity for computing in O(1) approximate maximum matching in a graph. The authors use the augmented hidden matrices (AHM) problem to establish this bound. The AHM problem is defined recursively, with each instance involving a matrix input for Alice and a bit input for Bob. The communication process involves Alice starting the conversation, followed by a series of messages exchanged between the two players. A search sequence is provided to the player receiving the last message, which helps in identifying the solution to the AHM instance. The paper shows that any dynamic streaming algorithm that uses n polylog, n, space to compute an O(1) approximate maximum matching must use at least log n passes. This is achieved by considering an AHM instance with p equals O, log n, and thus R equals 2p1 equals O, log n. The space used by the algorithm is then shown to be Sn polylog, n, using equation 19. Therefore, any semistreaming algorithm must use at least log n passes. The AHM problem is further explained in detail, including the base case for R equals 0, where Alice does not receive any input, and Bob receives a single bit. For r is greater than or equal to 1, the AHM problem involves b squared r many instances of the player's inputs in AHM R1, NR1, alpha, with Alice receiving a BR times BR matrix and Bob receiving a tuple containing permutations and another BR times BR matrix. The special subinstances and off-diagonal subinstances are defined, along with the search sequences that are used to identify the solution to the AHM instance. Overall, the paper establishes a lower bound on the space complexity for computing an O(1) approximate maximum matching in a graph using the AHM problem. This bound is crucial for understanding the limitations of dynamic streaming algorithms in graph theory. The paper discusses the augmented hidden matrix (AHM) problem, a fundamental problem in communication complexity. It presents a novel approach to solve the AHM problem using a recursive construction method. The authors define the AHM problem and its parameters, including the number of rounds, r, the size of the matrix, n, and the asymmetry parameter, alpha. They also introduce a hard distribution doctor, nr, alpha, for the AHM problem, which is crucial for the analysis of the communication complexity. The authors then prove a lower bound on the communication complexity of the AHM problem. They use a round elimination argument to show that if there exists a deterministic protocol for AHMR with low communication complexity, then there must be a deterministic protocol for AHMR1 with even lower communication complexity. This process is repeated until they reach the base case of AHM0, where they can use an observation to contradict the assumption of a low communication protocol. The paper also includes a detailed explanation of the parameters and the hard distribution used in the AHM problem. The authors provide an illustration of the AHM problem and explain how the search sequence is defined. They also discuss the limitations and future work related to the AHM problem. In summary, the paper presents a novel approach to solve the AHM problem using a recursive construction method and proves a lower bound on the communication complexity of the AHM problem. The authors provide a detailed explanation of the parameters, the hard distribution, and the limitations of the AHM problem, making this paper a significant contribution to the field of communication complexity. The proof for the base case when r equals 1 is established by showing that a deterministic zero-round protocol pi0 for AHM0, 1, has no communication cost and succeeds with probability suc pi0, 1/2, 1 plus 1/40th CADV, when the input is sampled from D0, 1. This contradicts observation 5.5, thus proving the result for the base case. For the inductive step, assuming the result holds for r-1, a deterministic protocol pi-r for AHMR, nr, alpha, with communication cost Cc, pi-r, less than SR and probability of success suc, pi-r, 1/2, 1 plus r, 20 CADV, r plus 1, is considered. Using lemma 5.6, a deterministic, r-1, round protocol pi-r-1 for AHMR-1, nr-1, alpha, with cost Cc, pi-r-1, less than CJP, 40 CADV, r plus 1, 2r, SR, Kr plus r, and probability of success suc, pi-r-1, 1/2, 1 plus r, 20 CADV, r plus 1, minus 1, 40 CADV, r plus 1, 2, minus RSR, 2b2r alpha 2 is obtained. The communication cost Cc, pi-r-1, is then bounded using the relation between nr and nr-1 from EQ, 20. By simplifying the expression for the term SR, Kr, it is shown that Cc, pi-r-1, less than CJP, 40 CADV, r plus 1, 2r, SR-1 1, CJP C2 adva 802, r plus 1, 3 plus r. This implies that Cc, pi-r-1, less than SR-1, which contradicts the inductive hypothesis. The probability of success suc, pi-r-1, is also bounded, and it is shown that suc, pi-r-1, 1/2, 1 plus, r-1, 20 CADVR. This contradicts the result for r-1, namely, the inductive hypothesis. The rest of the proof involves a careful calculation of the values obtained using the above reduction for the communication cost and probability of success of the protocol. The paper discusses the communication complexity of the approximate Hamming distance problem, AHM, in the multi-party number and hand model. It presents a round elimination argument to show that any deterministic round protocol for AHM with a certain communication cost and success probability can be transformed into a deterministic, R1, round protocol with a slightly higher communication cost and a slightly lower success probability. The authors first bound the communication cost of a deterministic protocol pi r1 constructed from pi r using a useful relation from equation 20. They simplify the term SR, 2b2r alpha 2, in equation 22, and plug it back into the equation to obtain a bound on the probability of success for pi r1. This bound is then used to show that the deterministic protocol pi r1 contradicts the lemma for r1, thus proving the lemma for deterministic round protocols when the input is sampled from the distribution doctor for every r is greater than or equal to 1. The paper also outlines the round elimination argument, which consists of 3 steps: input embedding, message compression, and guessing the first message. In the input embedding step, a randomized round protocol pi 1 r is constructed with a success probability similar to pi r and an internal information cost less than the communication cost of pi r by a kr multiplicative factor. In the message compression step, a randomized round protocol pi 2 r is constructed with a success probability less than that of pi 1 r by at most an additive epsilon factor and a communication cost similar to the internal information cost of pi 1 r under Dr. 1. Finally, in the guessing the first message step, a deterministic, R1, round protocol pi R1 is constructed with a success probability less than that of pi 2 r by at most an additive asymptotically equal PS B2R alpha 2 factor and a communication cost no more than that of pi 2 r. Here is a combined summary of the 2 pages. The protocol pi 1 r is an round protocol for the augmented hidden matching AHM problem, which is a variant of the hidden matching problem. The protocol involves 2 players, Alice and Bob, who take on the roles of players PX and PY in the simulated input instance of AHMR. The protocol uses public randomness to sample a uniform random search index K-star operator and jointly sample the following variables from the distribution doctor: NR, alpha, the uniform random permutations sigma r, sigma c of BR, Bob's part of all the K2R-Kr many off-diagonal subinstances BOF, Alice's part of K-star operator -1 many special subinstances aspect less than K-star operator, and Bob's part of Kr-K-star operator many special subinstances B-spec greater than K-star operator. The players then simulate a run of protocol pi r using their respective inputs A, R, equals X and B, R, equals sigma r, sigma c, y, and starting with player px. At the end of the protocol, the player that receives the final message gets the uniform random search sequence, K-star operator r-1, K-star operator r-2, K-star operator 0, and returns the answer of pi r on the search sequence, K-star operator r-1, K-star operator r-2, K-star operator 0. Observation 5.7 states that in protocol pi 1 r, A, R, B, R is sampled from Dr. NR, alpha, and K-star operator r-1, K-star operator r-2, K-star operator 0, is a uniform random search sequence. This is proven by showing that all variables of the input are jointly sampled from Dr. NR, alpha, except for Alice and Bob's embedded instance. A star operator, B star operator, tilde operator Dr. -1, NR -1, alpha, which is independent of all other variables in the distribution Dr. NR, alpha. Claim 5.8 proves that the internal information cost of pi 1 r about its input sampled from Dr. -1 is 1 kr times smaller than the information cost of pi r about its own input sampled from Dr. This is done by bounding the mutual information terms corresponding to the amount of information communicated by each player about their input. The proof involves using the definition of conditional mutual information and the uniform distribution of K-star operator to bound the mutual information terms. The notation used in the proof includes a star operator, B-star operator to denote the random variables corresponding to the input instance of AHMR-1 given to Alice and Bob, and pi to denote the random variable corresponding to the set of messages sent by both Alice and Bob. The proof also uses the notation AOF, BOF, K-star operator, aspect, B-spec to denote the random variables corresponding to AOF, BOF, K-star operator, aspect equals aspect 1, aspect 2, a specker, B-spec equals B-spec 1, B-specker, respectively. Here is a combined summary of the 2 pages. The authors continue to bound the mutual information terms in the protocol pi, 1, r. They first consider Alice's mutual information term, I, aspect, k, pi, sigma r, sigma c, bof, bspec is greater than or equal to k, aspect less than k, and show that it is upper bounded by 1, kri, aspect, pi, sigma r, sigma c, bof, bspec. This is done by applying proposition A.2 and the chain rule of mutual information. Similarly, they bound Bob's mutual information term, I, bspec, k, pi, sigma r, sigma c, bof, k equals k, bspec greater than k, aspec is less than or equal to k, by 1, kri, bspec, pi, sigma r, sigma c, bof, aspec. These bounds are then used to upper bound the LHS of EQ, 25. Which represents the internal information cost of the protocol. The authors then introduce lemma 5.9, which states that protocol pi, 1, r is an round protocol for AHMR-1, NR-1, alpha, with communication cost at most s, probability of success at least delta, and internal information cost at most s, kr. The proof of this lemma involves showing that the total number of bits communicated in pi, 1, r is at most the total number of bits communicated in pi r, and that the protocol outputs the same answer as pi r. The authors then describe a low communication cost protocol pi, 2, r, which is obtained by compressing the communication cost of pi, 1, r using standard message compression techniques. They show that the communication cost of pi, 2, r is upper bounded by CJP, r, epsilon, s, kr plus r, and that the probability of success is at least delta minus epsilon. This is done by applying proposition 3.13 to protocol pi, 1, r and using the bound on the internal information cost of pi, 1, r. The key concepts and methodologies used in these 2 pages include mutual information, conditional mutual information, and message compression techniques. The authors use these concepts to bound the internal information cost of the protocol and to obtain a low communication cost protocol. The equations and algorithms presented are used to derive these bounds and to describe the protocols. The figures and tables are not explicitly mentioned, but the text assumes a familiarity with the notation and concepts introduced earlier in the paper. Here is a combined summary of the 2 pages. The protocol pi, 2, r is constructed by adding an independent source of public randomness to pi, 1, r, which compresses the messages sent in pi, 1, r. This results in a smaller communication cost and a slightly smaller probability of success. The next step involves eliminating the first message by making the players guess it using public randomness, thus beginning the protocol from the second round. This alters the joint distribution of the input and affects the guarantees of the protocol. The R1 round protocol pi R1 for AHMR1 is constructed by embedding the input for AHMR1 into a simulated instance of AHMR. The players simulate a run of pi 2 r using the simulated instance, where the first message is guessed using public randomness. However, this random guessing of the first message means that the simulated instance is no longer distributed according to Dr. NR, alpha, and the guarantees of pi 2, r do not hold for pi r1. Despite this, it is shown that the simulated instance and first message are statistically close to being distributed as they are in pi 2, R, and similar guarantees hold. The joint distribution of the input and first message in pi r1, denoted as dfake, is compared to the joint distribution in pi 2, R, denoted as dreal. It is shown that the two distributions only differ in the way that the input, A star operator, B star operator, is sampled. The proof of claim 5.11 shows that the distributions dfake and dreal can be expressed as products of conditional distributions. By simplifying the expressions, it is shown that the two distributions are identical except for the conditioning of the input, A star operator, B star operator. The mutual information terms are bounded to prove that the corresponding terms in dreal are identical to those in dfake. The construction of the protocol pi r1 and the comparison of the distributions dfake and dreal are crucial steps in establishing the guarantees of the protocol. The results show that the protocol pi r1 is a valid, R1, round protocol for AHMR1, and the guarantees of the protocol are similar to those of pi 2, R. The paper discusses the information theoretic analysis of a specific quantum communication protocol, focusing on the mutual information between different components of the system. It begins by establishing a chain rule for mutual information, which is used to bound the mutual information between two sets of variables in the protocol. This bound is crucial for understanding the flow of information within the system and how it affects the overall performance of the quantum communication protocol. The authors then delve into the specifics of the quantum communication protocol, introducing concepts such as simulated instances, real instances, and fake instances. They provide a detailed explanation of how these instances are generated and their roles in the protocol. The main goal is to show that the total variation distance between real and fake instances is small, which implies that the protocol can efficiently simulate quantum communication without revealing too much information about the input. To achieve this, the authors use various claims and lemmas to bound the mutual information between different variables in the system. For example, claim 5.12 shows that certain variables are independent given specific conditions, while claim 5.13 provides a bound on the mutual information between a variable and a set of messages. These bounds are essential for establishing the desired properties of the quantum communication protocol. The paper also introduces partial definitions of permutations, such as tro and tcol, which represent ordered sets of rows and columns in a matrix. These definitions are used to further bound the mutual information and demonstrate the efficiency of the protocol. The authors provide an illustration of these definitions in Figure 10, which helps to visualize the relationships between different components of the system. Overall, the paper presents a comprehensive analysis of a quantum communication protocol, focusing on the information theoretic aspects and the flow of information within the system. The authors use various mathematical tools and techniques to establish the desired properties of the protocol, making it an important contribution to the field of quantum computing and communication. Here is a combined summary of the 2 pages. The authors present claims 5.14 and 5.15, which are crucial in bounding the mutual information between certain random variables. Claim 5.14 states that the distribution of bspec_k is independent of the permutations rho r and rho c conditioned on tro tcol rho r br alpha plus k and rho c br alpha plus k . This claim is proved by showing that the joint distribution of b r1 underscore I j for a fixed set of positions of a r and the transcript pi 1 is independent of the permutation of the rest of the positions of a r . Using claim 5.14, the authors bound the mutual information I bspec_k pi 1 sigma r sigma c z by conditioning on z tro tcol rho r br alpha plus k and rho c br alpha plus k . They then apply the definition of conditional mutual information and the linearity of expectation to obtain an upper bound on the mutual information. The authors re-index the sets br tro and br Tcol as br alpha plus 1 for ease of exposition, and use proposition A.2 to bound the mutual information I by j pi 1 z tro tcol They then apply the chain rule of mutual information, fact A.1, 4, and non-negativity of mutual information, fact A.1, 2, to obtain an upper bound on the mutual information. Claim 5.15 states that the information revealed by random variable raw about the input a star operator, b star operator, is not too large and real The authors proved this claim by showing that I aspec underscore k star operator, b spec underscore k star operator, raw equals I b spec underscore k star operator, raw plus I aspec underscore k star operator, raw b spec underscore k star operator, where the second term is 0. They then bound I b spec underscore k star operator, raw using the chain rule of mutual information and non-negativity of mutual information. The authors use these claims to establish an upper bound on the mutual information between certain random variables, which is crucial in their analysis. The technical details of the proofs, including the use of conditional mutual information, linearity of expectation, and chain rule of mutual information, demonstrate the author's rigorous approach to bounding the mutual information. In the context of machine learning and artificial intelligence, the paper discusses the augmented hidden matrices (AHM) problem, which is a fundamental problem in communication complexity. The AHM problem involves two players, Alice and Bob, who are given matrices A and B, respectively, and a search sequence. Their goal is to determine if the search sequence is in the intersection of A and B without revealing any additional information about their matrices. The paper presents a round elimination argument for the AHM problem, which reduces the number of rounds in the communication protocol while maintaining the probability of success and controlling the communication cost. This is achieved by using a combination of techniques, including the chain rule for mutual information, Pinsker's inequality, and Jensen's inequality. The authors also establish a connection between the AHM problem and the maximum bipartite matching problem in the dynamic streaming model. They show that any PPASSS space dynamic streaming algorithm that computes a beta approximate maximum matching on a bipartite graph can be used to construct an round protocol for AHMR with a non-trivial probability of success and controlled communication cost. The paper provides detailed mathematical proofs and explanations for these results, including equations, algorithms, and mathematical concepts. It highlights novel ideas, significant findings, and important arguments presented in the research, making it suitable for expert researchers and stakeholders in the field of machine learning and artificial intelligence. The paper discusses the construction of a bipartite graph using the alternating Hamiltonian matrix (AHM) model, specifically focusing on the AHMR model. This model is defined recursively, with each instance comprising b(r) many AHMR1 subinstances. Each of these subinstances has its own k(r1) many special subsubinstances, ultimately corresponding to the k(r)(r1) k(1) many special base instances, where each one corresponds to a single bit. The base instances or bits are represented in the graph using a basic bipartite graph construction called a bit graph. This graph has 4 vertices and encodes bits in the construction of G. The bit x can be identified by either of the edges in E. Given an instance, A, R, B, R, of AHMR, n_r, alpha, the paper provides a recursive procedure that separately encodes A, R, and B, R, as the edges of a bipartite graph on the vertex sets L and R. For ease of notation, L, I, and R, J, are defined as subsets of L and R, respectively, for I, J element of b(r). The edges added corresponding to the subinstance, A, R1, I, J, B, R1, I, J, will be only across vertices in L, I, and R, J. The construction of the graph is as follows. For R equals 0, when Z element of 0 1. Return the edges of the big graph corresponding to z for r is greater than or equal to 1. When z element of 1, n underscore r, 0, n underscore r, return the edges I, j element of b caret r, edges r1, z, l, I, r, j, where z is the n underscore r1 times n underscore r1 matrix with all its entries the same as the entries in z when z equals a, r, return the edges I, j element of b caret r, edges r1, b, r1, underscore I, j, l, I, r, j. When z equals b, r, return the edges I, j element of b caret r alpha less than sigma underscore r, I, does not equal sigma underscore c, j, is less than or equal to b caret r edges r1, b, r1, underscore I, j, l, I, r, j, union I, j element of b caret r alpha less than sigma underscore r, I, equals sigma underscore c, j, is less than or equal to b caret r edges r1, a, r1, underscore I, j, l, I, r, j. If r is even, in addition to the above, return the edges I, j element of b caret r, sigma underscore r, I, is less than or equal to b caret r alpha or sigma underscore c, j, is less than or equal to b caret r alpha edges 0, 1, n underscore r1, l, I, r, j, union edges 0, 0, n underscore r1, l, I, r, j. The paper also claims that for any r is greater than or equal to 0, given an instance, a, r, b, r, of ahmr, n underscore r, alpha, Alice and Bob can compute edges r, a, r, l, r, and edges r, b, r, l, r, respectively, without any communication. The proof of the claim is by induction on r, where the base case when r equals 0 is trivial. For any r is greater than or equal to 1, the player holding a, r, has access to all b, r1, underscore, I, j, for I, j element of b caret r. Thus, the player can construct the required set of edges r1, b, r1, underscore, I, j, l, I, r, j, for all I, j element of b caret r, without any communication. The construction of a bipartite graph G from an instance A, R, B, R of the asymmetric hypercube matching AHM problem is presented. The graph G is constructed recursively, with one player inserting edges and the other player deleting edges. The roles of the players, Alice and Bob, depend on the parity of R. Figure 12 illustrates the edges corresponding to A, R, and B, R, with orange edges representing the set of edges corresponding to the input B, R1, held by Alice, and blue edges representing the set of edges corresponding to the special subinstances A, spec, held by Bob. The dashed gray edges represent the set of no edges when R is odd and the set of all possible edges when R is even. The recursive definition of the graph construction is presented, where the player holding B, R, has access to permutations sigma r and sigma c. The player can construct the required edges without communication by the induction hypothesis. Additionally, when R is even, the player constructs edges corresponding to subinstances in B, rest, without any communication. The main procedure for constructing the graph G is presented, where one player inserts edges and the other player deletes edges. The particular roles of Alice and Bob depend on the parity of R. When R is odd, Alice inserts the edges and Bob deletes the edges, and when R is even, the roles are reversed. Figure 13 illustrates the constructed graph G, where the nodes on the left and right correspond to vertex groups L, I, and R, J, for each I, J element of BR. The edges represent the set of edges corresponding to the instance A, R1, B, R1, where a lack of edge implies that all edges inserted have also been deleted. Claim 5.19 states that the constructed graph G is a valid graph, namely, a del subset equal 1. The proof is presented by induction on R, where the claim is proven by showing that the player that inserts the edges and the player that deletes the edges depend on the parity of R. The claim is proven for the base case R equals 0 and for the inductive step when R is greater than or equal to 1. In the context of the alternating Hamiltonian model, AHM, we consider two different groupings of edges. For the first grouping, when Br alpha less than sigma R, I, equals sigma C, J, is less than or equal to Br, the edge set held by Bob is directly contained in the edge set held by Alice. For the second grouping, when Br alpha less than sigma R, I, equals sigma C, J, is less than or equal to Br, Bob holds the edge set and Alice holds the edge set. By the induction hypothesis, since R1 is even, we have that the edge set held by Alice is a subset of the edge set held by Bob. For even R, we have three different cases. When Br alpha less than sigma R, I, equals sigma C, J, is less than or equal to Br, the edges held by Alice are directly contained in the edges held by Bob. When Br alpha less than sigma R, I, equals sigma C, J, is less than or equal to Br, by the induction hypothesis as R1 is odd, we have that the edges held by Alice are a subset of the edges held by Bob. When sigma R, I, is less than or equal to Br alpha or sigma C, J, is less than or equal to Br alpha, the edges held by Alice are trivially a subset of the edges held by Bob. Overall, we have that a del subset equal 1 for any choice of R is greater than or equal to 0 and thus G equals L union R. 1, a del, equals graph A, R, B, R, is a valid graph. The players can take an instance, A, R, B, R, of AHM and construct a valid graph G without any communication. We define special vertices L-spec and R-spec. In the following claim, we show that the special vertices do, in fact, correspond to the special subinstances, A-spec, B-spec, of A, R, B, R. For R is greater than or equal to 1, the subgraph of G induced by the vertices L-spec union R-spec is exactly the vertex disjoint union of graphs graph, A-spec, B-spec, for all k element of Kr. We identify special base instances and their corresponding sets of special base vertices in L and R using tuples in Kr times Kr1 times K1. We denote this special base instance as Bs. Furthermore, we use A, B, to denote the collection of special base instances, as Bs, for all S equals SR, SR1, S1, element of Kr, times Kr1, times K1. Any tuple S equals SR, SR1, S1, also identifies the sets of vertices L-spec SR subset equal L and R-spec SR subset equal R. Then the sets L-spec SR1 subset equal L-spec SR and R-spec SR1 subset equal R-spec SR. And so on until identifying the sets of special base vertices L-spec S1 subset equal L-spec S2 in L and R-spec S1 subset equal R-spec S2 in R. We denote these two sets of special base vertices as Ls and Rs. We further define L equals S element of Kr times Kr1 times K1 Ls and R equals S element of Kr times Kr1 times K1 Rs. With this notation, we can now show that the special base vertices L union R correspond to the special base instances A, B, using claim 5.20. For R is greater than or equal to 1, the subgraph of G induced by the vertices L union R is exactly the vertex disjoint union of the big graphs graph, as Bs, for all S element of Kr times Kr1 times K1. In the context of the alternating Hamiltonian matching AHM problem, we are presented with a graph construction that utilizes a bipartite graph G equals graph A, R, B, R, to simulate a run of any PPASSS space dynamic streaming algorithm A for a beta approximate maximum matching. This construction is based on the concept of special base instances and their corresponding big graphs, which are used to identify the bits of these instances in the graph G. The key properties of this graph construction include the following. 1. The graph G is a vertex disjoint union of subgraphs HSpec, each of which corresponds to a special base instance. 2. Each subgraph HSpec is itself a vertex disjoint union of big graphs, which are matchings of exactly two edges that can be used to identify the underlying bit of the special base instance. And 3. Any beta approximate maximum matching in G identifies the bits of at least nr. 1, beta minus 2 alpha r, many special base instances in A, R, B, R. To prove these properties, the authors use an inductive approach, starting with the base case when r equals 0 and then showing that the properties hold for r is greater than or equal to 1. They also provide a protocol pi for any instance, A, R, B, R, of AHMR, NR, alpha, that simulates a run of any PPASSS space dynamic streaming algorithm A for a beta approximate maximum matching on the bipartite graph G. This protocol is used to prove lemma 5.2, which states that the AHM problem can be solved using a dynamic streaming algorithm. Overall, this section of the paper provides a detailed explanation of the graph construction and its key properties, as well as a protocol for solving the AHM problem using a dynamic streaming algorithm. These results are crucial for understanding the main theorem of the paper, which states that the AHM problem can be solved in O(n²) time using a dynamic streaming algorithm. Here is a combined summary of the 2 pages. The protocol pi for approximate hypergraph matching, AHM, R, NR, alpha, on input, A, R, B, R, using the PPASSS space dynamic streaming algorithm A is described. The protocol involves Alice and Bob simulating each pass of A on the stream of insertions sigma A followed by deletions sigma B, while exchanging messages to identify the labels of special base instances in A** operator, B** operator. The protocol consists of 4 steps. A. Computing edge insertions and deletions. B. Simulating each pass of A. C. Identifying special base instances. And D. Returning the output of the protocol. The protocol requires R rounds of communication, where R equals 2p1. The communication cost of the protocol is analyzed, and it is shown that CC pi is less than or equal to Rs plus O, R² nr log nr, where S is the space complexity of the algorithm A. The probability of success of the protocol is also analyzed, and it is shown that suc pi is greater than or equal to 1/2 plus 1, 6 beta, where beta is the approximation guarantee of the maximum matching returned by A. The protocol is used to prove the connection between maximum bipartite matching in the dynamic streaming model and the AHMR problem. The proof involves showing that the protocol pi is an round protocol with the desired communication cost and probability of success. The proof also relies on lemma 5.23, which states that the edges of the matching M returned by A identify the bits of at least nr. 1, beta 2 alpha r, many special base instances. The analysis of the protocol's communication cost involves bounding the number of bits sent in each round. It is shown that the total number of bits sent in R rounds is O, RNR log NR. The probability of success of the protocol is analyzed by considering the case where A succeeds in outputting a beta approximate maximum matching M. It is shown that M identifies the bits of at least NR, 1, beta 2 alpha r, many special base instances, and that the probability of success is at least 1/2 beta. The protocol's output is determined by the matching M returned by A and the identified labels of the special base instances. The output is either 0 or 1, depending on whether M contains certain edges. If M contains the edge L, R, or L, R, the output is 0. If M contains the edge L, R, or L, R, the output is 1. Otherwise, the output is a uniform random bit. The protocol's success probability is analyzed, considering 3 scenarios. When algorithm A succeeds and algorithm M correctly identifies the solution bit, when A succeeds but M fails, and when A fails. The probability of success is calculated as at least 1 minus 1, poly, n, 1/2 beta 1 plus 1 minus 1/2 beta, 1/2, plus 1, poly, n. 0 is greater than or equal to 1/2. 1 plus 1/3 beta, where beta is a constant. This concludes the proof. The construction of graph A, R, B, R is discussed, highlighting the difference in behavior when R is even versus odd. When R is even, Alice deletes edges before Bob adds them, which is not consistent with the definition of dynamic graph streams. However, in the construction, only the AHMR lower bound is used when R equals 2p-1, which is odd. In this case, Alice adds edges to the graph, and Bob deletes them after all edges are added, adhering to the restriction of dynamic graph streams. The references provided cover various topics in graph streaming algorithms, including semistreaming maximum matching, multipass graph streaming lower bounds, and polynomial pass semistreaming lower bounds for K-cores and degeneracy. Other references discuss correlation clustering in data streams, linear programming in the semistreaming model, and access to data and number of iterations in dual primal algorithms for maximum matching under resource constraints. The list of references also includes papers on analyzing graph structure via linear measurements, semistreaming bipartite matching in fewer passes and optimal space, and the stochastic matching problem with few queries. Additionally, papers on estimating maximum matching size in graph streams and polynomial pass lower bounds for graph streaming algorithms are mentioned. The references demonstrate the author's engagement with the broader research community, citing works from various conferences and journals, including SODA, ICML, STOC, and Approximately, Random. The citations also highlight the author's contributions to the field, with multiple papers listed as to appear or in press, indicating ongoing research efforts. The paper discusses various algorithms and techniques for solving graph problems in streaming models, focusing on dynamic graph streams and the simultaneous communication model. It highlights the importance of these models in real-world applications, such as social networks and web graphs, where data is constantly being updated. The authors present several algorithms for solving maximum matching and vertex cover problems in these models, including a single-pass semistreaming algorithm for delta coloring and a multipass algorithm for finding a maximal independent set. They also discuss lower bounds for these problems, showing that certain algorithms are optimal in terms of the number of passes required. In addition, the paper explores the use of kernelization via sampling with applications to finding matchings and related problems in dynamic graph streams. This approach involves reducing the size of the input graph while preserving the solution to the problem, making it more efficient to solve. Furthermore, the authors examine parameterized streaming algorithms for solving vertex ordering problems in directed graph streams. These algorithms are designed to work within the constraints of the streaming model, where the input graph is presented one vertex at a time. The paper also covers recent advances in superconstant pass streaming lower bounds for reachability and near-optimal two-pass streaming algorithms for sampling random walks over directed graphs. These results demonstrate the ongoing research efforts to improve the efficiency and accuracy of algorithms in these models. Overall, the paper provides a comprehensive overview of current research in graph algorithms for streaming models, highlighting both the challenges and opportunities in this area. It emphasizes the importance of developing efficient algorithms that can handle large, dynamic graphs and discusses potential applications in various fields. The paper discusses the challenges of approximating maximum bipartite matching in the streaming model, where edges arrive one at a time and cannot be revisited. The authors provide a comprehensive overview of previous work on this problem, including algorithms and lower bounds for both one-pass and two-pass streaming models. They highlight the importance of understanding the trade-offs between the number of passes and the approximation ratio achieved by algorithms in this context. The authors also discuss the role of communication complexity in understanding these trade-offs, as it provides a framework for analyzing the amount of information that must be exchanged between different parts of an algorithm to achieve a certain approximation ratio. The paper then presents new results on two-pass streaming algorithms for maximum bipartite matching, including an unconditional lower bound for any two-pass algorithm. This lower bound is based on a novel reduction from a communication complexity problem, which demonstrates the power of this framework in understanding the limitations of streaming algorithms. Finally, the authors discuss future directions for research in this area, including the potential for developing new algorithms that can achieve better approximation ratios than current state-of-the-art methods. Overall, The paper provides a thorough exploration of the challenges and opportunities in approximating maximum bipartite matching in the streaming model, shedding light on the complex interplay between algorithm design, communication complexity, and the constraints of the streaming model. The paper discusses various algorithms and techniques for solving graph problems, particularly focusing on the semistreaming model. It begins by introducing the concept of a simple augmentation method for matchings, which has applications to streaming algorithms. This method is further explored in the context of adaptive steps toward the multiphase conjecture. The authors also delve into filtering, a method for solving graph problems in MapReduce, and its implications for parallelism in algorithms and architectures. They discuss unconditional pseudorandom generators for low-degree polynomials and their relevance to matching theory. The paper then shifts its focus to data structures and asymmetric communication complexity, highlighting the importance of randomized algorithms and their role in distributed and streaming computations. It presents optimal lower bounds for distributed and streaming spanning forest computation, as well as randomized distributed edge coloring via an extension of the Chernoff-Hofding bounds. Furthermore, the authors explored triple systems with no 6 points carrying 3 triangles, a concept that has been studied since the late 1970s. They also discuss communication complexity and its applications, emphasizing the importance of limited independence in Chernoff-Hofding bounds. Finally, the paper concludes with deterministic algorithms for maximum matching on general graphs in the semistreaming model and the growth of a random maximal independent set, which produces a 2-approximate vertex cover. Throughout the paper, the authors provide a comprehensive overview of the current state of research in these areas, highlighting novel ideas, significant findings, and important arguments. This section provides a background on information theory, introducing definitions and facts necessary for the thesis. It begins by defining the support and distribution of a random variable A, denoted as sup A, and dist A, respectively. The Shannon entropy of A is defined as H A equals underscore a element of sup A. PR A equals A log 1 PR A equals A, which measures the uncertainty or randomness of A. The conditional entropy of a given B is denoted as H A B and defined as E underscore B tilde operator B H A B equals B, representing the uncertainty of a given. The value of B mutual information between A and B is defined as I A B equals H A B equals hydrogen boride H B A, quantifying the amount of information that it contains about B. Several useful properties of entropy and mutual information are presented, including non-negativity of entropy, non-negativity of conditional mutual information, and the data processing inequality. 2 propositions are also stated, which describe the effect of conditioning on mutual information. Proposition A.2 states that if A is independent of D given C, then conditioning on D does not increase the mutual information between A and B given C. Proposition A.3 states that if A is independent of D given B and C, then conditioning on D does not decrease the mutual information between A and B given C. The section also introduces 2 measures of distance between distributions: the Kullback-Leibler (KL) divergence and the total variation distance. The KL divergence between 2 distributions mu and nu is defined as d mu nu equals E underscore a tilde operator mu log mu a nu a, which measures the difference between the 2 distributions. The total variation distance between mu and nu is defined as parallel mn underscore tvd equals max underscore omega subset equal omega mu omega nu omega, which represents the maximum difference between the probabilities assigned by mu and nu to any event. Fact A.6 states that for any distributions micro and nu on n tuples x1 xn, the total variation distance between these distributions is bounded by the sum of the total variation distances of their conditional distributions. This fact is crucial in understanding how the total variation distance behaves under conditioning. Fact A.7, also known as Pinsker's inequality, provides a bound on the total variation distance between 2 distributions based on their Kullback-Leibler (KL) divergence. This inequality is significant because it establishes a relationship between two different measures of distance between probability distributions, allowing researchers to leverage information about one measure to make inferences about the other. These facts are essential tools in the analysis of probability distributions and their relationships. They have applications in various fields such as machine learning, information theory, and statistical inference. For instance, in machine learning, understanding the total variation distance and KL divergence can help in assessing the similarity between different models or the convergence of an algorithm towards a target distribution. In statistical inference, these facts can be used to construct tests for hypotheses involving the equality of two distributions. By bounding the total variation distance using Pinsker's inequality, researchers can determine the maximum possible difference between two distributions given their KL divergence, which aids in setting thresholds for statistical tests. Furthermore, these facts highlight the importance of considering both the total variation distance and KL divergence when comparing probability distributions. While the total variation distance provides a measure of the maximum difference between two distributions, the KL divergence offers insights into the average difference. By utilizing both measures, researchers can gain a more comprehensive understanding of the relationships between different distributions. In conclusion, facts A.6 and A.7 are fundamental results in probability theory that have far-reaching implications for various fields. They provide essential tools for analyzing and comparing probability distributions, enabling researchers to make more accurate inferences and develop more effective algorithms.